Cystic fibrosis is one of the most common genetic diseases in humans. Approximately 1 in 25 people carries a cystic fibrosis gene. And when both parents carry a faulty gene, there is a 25% chance that their child will have cystic fibrosis. In the early 1980s, biologists started a hunt for cystic fibrosis genes, one of the first gene hunting projects in the framework of the Human Genome Project. 30 years ago, biologists narrowed the search for the cystic fibrosis gene to a million nucleotide long region on chromosome 7. However, this region contained many genes, and it was not clear which of them is responsible for cystic fibrosis. How would you find which of these genes is the cause of cystic fibrosis? I'll give you a hint. Cystic fibrosis involves sweet secretion with abnormally high sodium level. Well, this is a biological hint that does not help us to solve the challenge of finding something in this 1 million nucleotide area that is responsible for cystic fibrosis. Let me give you hint number 2. By that time, when cystic fibrosis hunt was on, biologists already knew the sequences of some genes responsible for secretions. For example, ATP-binding proteins act as transport channels responsible for secretion. You still may be wondering how these two hints may help you to find the cystic fibrosis gene in the found 1 million nucleotide wrong region on chromosome 7, but here's my third hint. Should we search for genes in this region that are similar to known genes responsible for secretion? Biologists used this third hint, and bingo, they found that one of the genes in this region was similar to the ATP-binding proteins that act as transport channels responsible for secretion. To learn how biologists find similarities between genes, we will first learn how to play a simple game called the alignment game. The alignment game is a single-person game. I give you 2 strings, and your goal is to remove symbol from the strings in such a way that the number of points is maximized. I have to explain you how you can get point for playing the alignment game. You can either remove the first symbol from both strings, and in this case you get 1 point if there's the same symbol. You don't get any points if they're different symbol. Or you can remove first symbol from one of the strings, and in this case you also don't get any points. So let's try to play this game. In the beginning it makes sense to remove the first symbol from both strings. We'll get +1, then another pair of identical symbol, another +1, and now symbols are different, so it doesn't make sense to remove them both because we'll get 0 point. Maybe we should only remove C from the second string, and after we've done this, there is a possibility to remove 2 G's from both strings. We get another point, we continue, and finally, after playing this game, we get score +4. Do you think you can get score +5 playing this game? We also, after playing this game, we constructed something that is called alignment of 2 strings. Alignment of 2 strings is a 2-row matrix such that the first row consists of symbols of the first string in order, possibly interspaced with the space symbol. And the second row consists of the symbols of the second string, once again possibly interspersed with the space symbol. After we constructed the alignment, we can classify different columns in the alignment matrix as matches or mismatches or insertions insertions correspond to the case when we selected a symbol from the second string, and deletions that correspond to the case when we selected the symbol from the first string. And moreover, we can score this alignment by giving premium for every match. We will give premium +1, and penalty for every mismatch and every insertion and deletion that we denote as indel. In our case, we will use penalty -mu for mismatches and penalty -sigma for insertions and deletions or indels. For example, in our case, if mu equals 0 and sigma equal to 1, then we get alignment score equal to 1. So we define the alignment score as the number of matches minus mu, number of mismatches, and minus sigma, number of indels. And the optimal alignment problem is, given two strings, mismatch penalty mu and indel penalty sigma, find an alignment of two strings maximizing the score. We will be particularly interested in one particular score of alignment. We will define common subsequence as simply matches in an alignment of two strings. In this case, common subsequence is represented by AT-GT. And the longest common subsequence problem that we will be interested in is the following. Given two strings, we want to find a longest common subsequence of these strings. And of course, you have already recognized that to find longest common subsequence, we simply need to find maximum score alignment with these parameters mu equals 0 and sigma equals 0. Another classical problem in computer science is the edit distance problem. Given two strings, find the minimum number of elementary operations, insertions, deletions, or substitutions of symbols that transform one string into another. And of course, the minimum number of insertion, deletions, and mismatches in an alignment of two strings represents the edit distance. For example, if we want to find the edit distance between the strings editing and distance, we can construct optimal alignment of the string with appropriate scores. Here I showed matches, mismatches, insertions, and deletions. And to see that the edit distance problem is equivalent to the alignment problem, let's consider this alignment between editing and distance, and let's compute the total number of symbols in two strings. Obviously, the total number of symbols in two strings is equal to twice number of matches, plus twice number of mismatches, plus number of insertions, plus number of deletions. I will take a liberty to rewrite this expression, and after I rewrote it, you will see that the first three terms correspond to the alignment score, and the last three terms corresponds to the edit distance. Therefore, minimizing edit distance is the same as maximizing the alignment score, which means that edit distance problem is just one particular version of the alignment problem.